Hello everyone, my name is Tiffany Roberts and this is my Lab 5 presentation. Felix was reported to have broken the speed of sound by jumping out of a balloon at an altitude of 120,000 feet. In this lab, I'm trying to recreate this event with my knowledge of physics principles and analyze how the atmosphere affects the outcome of his jump. Here is my plan to analyze the jump. I begin with defining the jumper and move to determining the model's equations. Then I have to understand the sound barrier and move forward with the code and methods. Then I'm looking at the following with the constant atmospheric conditions, following with change in temperature, and following with temperature and air density variance, looking at the results and determining whether or not Felix's jump is fact or fiction. I measured an individual in real life to represent the characteristics for the calculations. Using the dimensions of his waist and bicep size, I was able to create a cross-section analysis using a rectangle and circles. The drag force equation in this lab is my choice for modeling air resistance felt by Felix in his jump. The main components of this equation are the coefficient of drag, which is given experimentally in the chart on the right as 0.7, noting that the skydiver is feet first, rho, the density of air, v, the velocity updated continuously, and a, which is referring to the area of the individual we are calculating. Also taken into account are the position and velocity update equations, and just noting that in order to break the speed of sound at sea level, velocity must go beyond 344 meters per second. An important note about the speed of sound. Speed of sound is not constant. It is dependent on the ratio of specific heats, the specific gas constant, and absolute temperature. The full formula is shown in red in the figure on the right, and can be approximated to 344 meters per second at sea level. Here I begin to break down my code. The person, trail, and origin are created for visual display and data storage. Two plots are then created, one for position versus time and one for velocity versus time, and the last line initiates a red line for tracking the speed of sound that will be plotted on the velocity versus time chart. Here I am pointing out key values and initializations, the mass of a friend of mine, the jump height of the simulation and initial position and velocity of the skydiver, the start time and time increment, the value of g near the Earth, the experimental value for drag coefficient shown in the previous table, calculated A based on friend's waist cross-section, rho initialized for sea level, and the temperature initialized for sea level. Here we are looking at the while loop and rho variance. The while loop is started with the end condition of skydiver reaching the ground, and the sequence of if statements shown is used to vary the air density, rho, as the skydiver's altitude decreases. I was able to find a chart that represented the U.S. Standard Atmosphere Air Properties in SI units online. This table of atmospheric values is directly used for both the air density, rho, variance with altitude and temperature variance with altitude. The only translation from chart to code will be seen in the following slide, with temperature values being converted to Kelvin from the given Celsius unit. The height jump was also capped at a given value of 30,000 meters. Here we are looking at the temperature variance in the speed of sound. This set of if statements functions the same as for rho, but now for temperature. Immediately after the temperature is determined, the speed of sound is updated based on the previously shown equation. Here, the acceleration due to gravity, g, is permitted to vary according to altitude. However, it was determined through multiple trials of code that no noticeable difference on predictions is made by the variance of g, and is therefore not considered as part of results comparison. Following this, the drag force equation is implemented and is combined with the force of gravity to produce the net force. Here I am breaking down the code's updates and visuals. Newton's second law is implemented to update the skydiver's position and velocity due to the net force. Next, the time, trail, and plots are updated based on current calculated values. And finally, the forces of drag and gravity are visualized to better aid physical understanding of the simulations. How high should he jump if he wants to break the sound barrier in freefall? Here are the position versus time and velocity versus time charts, assuming t and rho are constant. The terminal velocity of the skydiver under sea level conditions is seen to be approximately 150 meters per second. Unless conditions vary, the skydiver will never reach the speed of sound, no matter how high they jump from. What effect does a change in temperature with altitude have on your predictions? Here are the position versus time and velocity versus time charts with t varied and rho constant. The terminal velocity of the skydiver remains 150 meters per second since the drag force equation used is not directly affected by temperature change. However, the speed of sound is noticeably affected at high altitude, lower temperature. The speed of sound is slower. The skydiver comes slightly closer but still will never fall fast enough no matter how high they jump from. What effect does a change in the density of air with altitude have on your predictions? Here we are looking at both position and velocity charts as t and rho are varied. Variance in rho has affected the skydiver's velocity greatly. The variance allowed the skydiver to reach the speed of sound at approximately 40 seconds when jumping from a height of 16,500 meters. Higher jump heights lead to even greater speeds which fully cross the threshold for the speed of sound. Felix's record is therefore fully plausible since his jump was from a height of approximately 36,000 meters. Just for fun, I chose to test the code with Felix's actual jump height of 36,000 meters. Looking at the interesting velocity versus time graph, it seems Felix nearly reached terminal velocity around 50 seconds, then immediately continued to speed up, breaking the sound barrier at about 65 seconds, and continued to even higher speeds. However, these findings are subject to possible great variance from Felix's actual jump, since in reality air density is a continuously varying value, rather than a stepped value as has been done with the code. This concludes my presentation. Thank you so much.